Well, as promised, we are now going to get into energy discussions with our mass spring system. And if you recall our potential energy, kinetic energy, total energy calculations from a few modules back, this is probably all going to look very, very familiar to you. So we've got our old friend, the mass spring system up here again, and I already have everything labeled. We know that at equilibrium, the restoring force is 0, so we know that the acceleration is going to be 0 because of Newton's second law, force equals mass times acceleration. And we had said that at this particular point, the velocity is at a maximum. To the converse of that, at the amplitude, we know that the restoring force is at its maximum. We know that the acceleration, therefore, will also be at a maximum, and the velocity here is going to be 0 because it is going to be changing direction at this point. It's going to come down this far, it's going to come to a stop, and then it's going to start going back the other direction again. Probably not totally unlike if you've got a projectile and it goes up in the air and it comes up here at some point. The velocity is actually a 0 up at that very top point because it's got to change from going up to then falling back down. So you can kind of think of this in the same way. He gave you the equations for potential energy for a spring. Potential energy is 1/2 times K times delta X, the quantity squared. Kinetic energy doesn't look any different than it did before. And then we know that the total energy is going to be the sum of the kinetic energy plus the potential energy at any particular point in time. Now, if you've taken this spring and you've stretched it down here and you're holding it here, it is not moving at that point. All the energy that it has at this particular point in time is potential energy, and the furthest away it is from equilibrium is when it is at its max because it's at its maximum distance. So at the amplitude, the potential energy is at its max, and kinetic energy is going to be equal to 0 because it is not moving at that point. Now, once you let go of it, the restoring force acts on it and it starts pulling it back up towards equilibrium. Okay, here your restoring force is 0, but what's the case here? Well, here it doesn't have any potential energy anymore because the delta X, the displacement from equilibrium, is 0, so that means your potential energy is going to have to be equal to 0. However, you can't just get rid of energy, it doesn't just disappear. So what that means is that at this particular point in time, your potential energy has been completely converted to kinetic energy. So at the equilibrium position, your kinetic energy is at its maximum. Okay, so the kinetic energy plus the potential energy is going to be the total energy at any point in time. And they say that that's equal to 1/2 Ka squared, where A is equal to your amplitude. Now, that should make sense because the amplitude is going to be the maximum amount of displacement. And so in this potential energy equation, this delta X actually is equal to the amplitude. At this particular point, your potential energy is at its max, kinetic energy is 0, so the total energy of the system when it's at this amplitude is going to be equal to whatever the potential energy is. And so this delta X is the amplitude. And so that's why I can say kinetic plus potential is 1/2 Ka squared. Okay, so we have these 3 equations to work with. And so now we're going to look at example 10.4, and so we can work through that. Okay. So example 10.4 says, in stretching an 11.2 kilogram mass on a spring, a physicist does 35 joules of work. What is the spring constant if this work stretches the spring 14.1 centimeters? If the spring were let go, what is the maximum kinetic energy it could have, and what speed would the mass have at that point? Well, there's 3 questions here. Let's take them one at a time. Let's start out by writing down exactly what we already know. We know that the mass is 11.2 kilograms. We know that the work, and I'm actually going to write work this time so we don't confuse it with weight. The work that she does on the spring as she's pulling it down is 35 joules. And we know that when she stretches the spring, once she hangs the mass on the spring, it stretches 14.1 centimeters. And as we've done before, I'm going to go ahead and change that to meters because I know that I'm going to have it in meters anyway to be able to work with it. Okay, so the first question that I'm asked is what the spring constant is, which if I'm going to be working with the spring and you don't know what the spring constant, that's going to have to be your first step regardless. Now, if this is the amount that the physicist has stretched the spring, I know that however far she stretches it, it's not going to go any further than the point to which they stretched it. So this delta x is also going to be equal to the amplitude. Okay, so I can then calculate the amount of potential energy it has, because all of this work that she does on the spring is going to be transformed into the potential energy of the mass once she lets go of it. So the potential energy is going to be equal to the work that she did on it, because she's translating. Remember, we can translate work into different kinds of energy. So all that work is turned into potential energy. Potential energy is 1/2 times K times delta X squared. Okay, so 35 joules is how much potential energy this is going to have. So I'm going to have 1/2 times K times 0.141 meters, and then I'll have to square that. And then so K is going to be equal to, when you solve that, K is going to be equal to 3,500 newtons per meter. Okay, so now I have the spring constant. Again, what I did here is I said all the work that she put into stretching it, all that is going to get converted to the potential energy of the spring when it is at its amplitude. So that's why I can take this and plug it into the potential energy equation right here. Okay, delta X, we said again, the amount she stretches it is equal to the amplitude, because it can't get any bigger than the amount she stretches it at. So the delta X is going to be equal to the amplitude. Okay, second question says, if the spring were let go, what is the maximum kinetic energy it could have? Now, I want to give you a shortcut here. He actually works it out. He knows that, and as you know as well, all this potential energy is going to be converted to kinetic energy. So I could actually calculate what that's going to be, but I could also just use my head for a minute and think. Because if it's asking me for the maximum kinetic energy, well, the maximum kinetic energy is what it's going to be at the equilibrium position. The maximum kinetic energy is what I'm going to have when the potential energy is equal to 0. Well, at the amplitude, I have the exact opposite situation, where the potential energy was at its max and the kinetic energy was equal to 0. So if I knew what the potential energy was at the amplitude, which was 35 joules, once it gets to the equilibrium position, all the potential energy has been converted to kinetic energy, yes? So therefore, the maximum kinetic energy is going to be the same as what the potential energy was at the amplitude. So therefore, the maximum kinetic energy is also going to be 35 joules. So I don't really have to calculate that out. I can just use my head and say, well, if all the potential is going to go to kinetic, then that's what it's going to have to be. Okay. Then the question is, what speed would the mass have at that point? Well, at that point, then I can use my old friend, kinetic energy is 1/2 mv squared, and kinetic energy is 35 joules. I have 1/2 times the mass was 11.2 kilograms times v squared. When I solve for v, I get 2.5 meters per second as my velocity. Okay, so I was able to calculate K. I knew that potential energy and kinetic energy, I knew that it was going to be a complete conversion, so I was able to do that without any calculations. You could calculate it, but it wasn't necessary. And then once you know that, then you can calculate what the velocity would be. And so again, this is going to be the velocity at equilibrium because that's where both the kinetic energy and the velocity are at their maximum. Okay, now we want to look at the second part of this example. And in this part of the example, we're looking at it when it's not at equilibrium and it's not at its amplitude position. So let's get rid of this information here so we've got some space to work. Whoops, don't want to erase that. Okay, let's put the kinetic energy back up here. Don't want to lose him. All right, now let's look at the second part of this problem. A 23-gram mass is placed on a spring, K of 46 newtons per meter. If the spring is stretched 12.3 centimeters and released, what will the mass's speed be when it is 8 centimeters from its equilibrium position? Okay, so again, we're going to start just by listing what we know. We know that we have a mass of 23 grams, but I also know that leaving it in grams isn't going to help me any. I need to convert that to kilograms. That's going to be 0.023 kilograms in SI units, which is what I'm going to need. I was told that the spring constant is 46 newtons per meter. I know that the delta X when the spring is stretched is 12.3 centimeters. And again, I'm going to go ahead and convert that to meters as well. Okay, I want to know what is the velocity when the delta X is at 8.0 centimeters. That's what the question is, okay? And so again, I can go ahead and convert this to meters because it's going to have to be in meters anyway, so it's going to be 0.080 meters. So I'm going to lose my significant figures there. So what is the velocity at that point? All right. In order to calculate this, I'm going to use this kinetic energy plus potential energy is 1/2 Ka squared because this is the equation for total energy of the system, okay? I know that kinetic energy is 1/2 mv squared, okay? I know that potential energy is this 1/2 K delta X quantity squared. And I know that when I add them together, it has to be 1/2 K amplitude squared, okay? Now again, this is a little bit different than he works it in the book, but what I did is I'm going to take this equation for total energy and I'm going to plug everything into it and I'm going to do it in one fell swoop, okay? So what I want to know is what is the velocity? So I know 1/2. I know that my mass is 0.023 kilograms. I don't know what the velocity is. That's what I'm trying to find. The potential energy is 1/2 times K, 46 newtons per meter. At a particular delta X, well, the delta X is 0.080 meters because that's the specific point that I'm talking about right here. So the potential energy at 8 centimeters plus the kinetic energy at 8 centimeters has to equal the total energy. So that's why I'm going to use this particular delta X because that's the particular point in time that I'm talking about. Okay, equals 1/2 times the K is again 46 Newton meters. And the amplitude was the delta X that I had when it was stretched at its max, which is this 12.3 centimeters or 0.123 meters. And then that has to be squared. Shoot, we almost ran out of space there, didn't we? All right, so I have all of this in here. Now it's just a matter of plugging in the numbers and chugging out the answer. And so once you do all that math, you are going to end up with a velocity of 4.2 meters per second. Okay, so again, it's just an arithmetic problem at this point, and so you get a velocity of 4.2 meters per second. So whenever you're working these problems where they're asking you at a point where you're somewhere in between the equilibrium and the amplitude, remember that this side of the equation is giving me the total energy, and so the amplitude is the amount that it was stretched when the weight's just hanging on it, which is going to be this one right here. And the potential energy and the kinetic energy are at the point where it's somewhere here in the middle, and that's what you're trying to calculate. So when you use the potential energy portion of this formula, you've got to use the distance that it is at that particular point in the period that you're discussing. So the kinetic energy at that point plus the potential energy at that point equals the total energy for the whole thing. Okay? So again, you'll get plenty of practice working some of these problems.